Okay, thank you for the introduction. I'm happy to have this opportunity to talk about our investigation into the systematic differences between current molecular dynamic force field to represent local properties of intrinsically disordered proteins in the monomeric forms. So a brief introduction to intrinsically disordered proteins and protein regions. This system we are interested in IDPs and IDRs. They are different from globular protein in that they don't adopt well-defined 3D structures. As you can see, the alpha-synuclein peptide, as you viewed in the ensemble bundle, is more like spaghetti. And example of IDR, the FG loop in the calcium binding domain is missing in the crystal structure. Despite that, the intrinsic disorder is ubiquitous. More 30% of eukaryotic proteins have more than 40 consecutive disorder residues, and they are linked to neurodegenerative diseases such as Alzheimer's and Parkinson's. And the interaction with the globular proteins are important in the molecular signaling and so on. But because they are unstructured in nature, the experimental characterization is very challenging. So this is where molecular dynamic simulation comes in. So MD simulation is basically just applying Newton's equation motion in its classic form, of course, again, and from the MT trajectory, you can extract atomic detail and dynamic information. But the accuracy of the MD simulation depends heavily on the accuracy on the force field. It usually takes a form of additive sum of different energy functions, bound angle dihedrals. One difficulty in the simulating AEPs using MD is that it sometimes give you incorrect structural characteristics, such as the backbone section propensity, soul bridges, and so on. So for that, we utilized coil library statistics and developed a residue type specific force field amber FF99 SB-NMR2, mainly by optimizing the dihedral function. So here we are gonna use IDP peptides alpha-synuclein and amyloid beta, two IDPs to do the benchmark. First, we're gonna kind of cleave them into overlapping peptides just to promote more better sampling, because those IDPs can be very large. And from that, we use experimental nuclear magnetic resonance 3J coupling constant to do the validation. So the power of 3J couplings is that it can link your structure information, the populations in the Ramachandra plot, alpha R, beta, PB2, alpha L, and so on, to the J-coupling constant using empirical couplers equations. So different region give you different range of J-coupling constant. For example, the peak of beta region give you around 8 Hertz, the alpha RPB to around 4 Hertz. We are calculating the middle three, calculate the J-coupling for the middle three residues for each peptide and compare with the experimental J-coupling constants. So here's the result. We have 4 force fields. Besides the NMR2 force field I talked about, there are Amber FF14SB, Charm 36M, and Amber 99SB disk. And on the y-axis is this predicted J-coupling, on the x, the experimental value. So the prediction error ranges from, in terms of MSD, 0.51 Hertz for NMR2 best to around 1 Hertz for the rest. And the Pearson correlation function for NMR2 result is also the highest, about 0.7. In addition, there's a general underestimation of the J-couplings in the rest of 3 force field. So those data points are overall below the diagonal line. So we wanted to understand what's the reason behind those underestimation. So we compare those the Ramachandra population of one force field from one force field to NMR2. So for example, we can look at the beta population for each residue as they were generated in the, say, FF14SB, how they compare to NMR2. We can also do that for the other two, alpha R and PB2. We are neglecting alpha L because it's usually a very low population. We can do the same for CHARM36M and 99SB disk. So there are numbers in two numbers in each figure. So they are the percentages of the data points above and below the diagonal. For the Amber 14SB, 100% of the beta population is underestimated when comparing to NMR2. In general, that's true for CHARM36M and 99SB disk also. And they are offset for FF14SB by an increase in alpha R population, so 98 over 2%. For CHARM36M, that's compensated by increase in mainly by the PB2 region population. For the 99SB disk force field, they are increased in both regions, alpha R and PB2. So when we looking back to the couplers curve, that kind of makes sense because the region you are underestimating, beta region, gives you in general highest J-coupling. So that's why we are seeing the underestimation in the J-coupling earlier. Finally, we group those residues by their residue types, and we can produce kind of residue-specific prediction error for each force field and generate those profiles. So the blue is the NMR2 force field. It gives you relatively consistent in a low MSD around 0.5 Hertz across all residue types. And we see for some residues types such as alanine, all force field give you a good result. But for some others, say valine, isoleucine, and so on, you can see the large variations in the MSDs. So that does speak to the power of residue-specific corrections in the force field optimization, and it also gives information for the force field development. So in summary, our new residue-specific force field NMR2 improves backbone dihedral angle ensembles for IDPs, and Amber 14SB, CHARM36M, and FF99SB disk force field systematically underestimate the beta region population in the Phi-side distribution. If you're interested in this force field, it can be downloaded from our group website. All the simulation will perform at the Ohio Supercomputer Center. Thank you for your attention. I'm happy to take any questions.